I needed a little bit of extra time to look at the period relationships, so we're going to take a look at that now. All right, so the idea here, notice that the normal period of a sine function, or a cosine function for that matter, is 360 degrees, okay? In other words, and if you think about the unit circle, you basically get around one circle and then your whole pattern repeats. And that's probably something I should look at a little bit more as well, the comparison between the unit circle and this curve. But anyway, more on that later. Anyway, the big idea here is that if I, for example, multiply x by a number, if I do sine of 2x, notice that the period changes, okay? Well, let's look specifically at how the period changes. It looks like we have more cycles, basically. But let's look at the period. The period was 360 degrees. Notice the period is now 180 degrees. Okay, so multiplying by 2 made the period drop from 360 to 180. Okay, let's go back to sine of x. So the period is 360 degrees again. Okay, let's do a 3x here, and let's look at what happens to the period. So now notice, to go through one cycle, the period is now, that's going to be 120. It's not marked very well, but the period went from 360 degrees to 120. Okay, when I multiplied by 3. Let's take a look if I multiply by 4. Okay, if I multiply by 4, the period is going to become 90 degrees. Okay, so the original period is 360. If I multiply by 2, it becomes 180. If I multiply by 3, it goes from 360 to 120. If I multiply by 4, it goes from 360 to 90. Okay, if you think about what's that relationship happening there, you're really dividing the period of 360 by whatever this multiplier is, okay? The other thing that you could think about is this multiplier out here really means that the sine function is moving 4 times as quickly. In other words, normally, for example, if you take sine of 360, you end up getting 0 if you substitute that in. Now, to get a 0 back, you don't have to put a 360 into here anymore. You can put a 90 in there because 4 times 90 will give you that 360. So because x is being multiplied by 4, you can put in an x that's a fourth as big. And what that's doing is that's narrowing down off camera here. It's narrowing down that range. It's making the graph a fourth as wide, or you could think of it as moving 4 times as quickly, okay? If I use a decimal, if I do like 0.5, okay, notice the period now is 720. This graph is moving half as quickly. You would have to put an x value in that's twice as big to get the same result you got before. So for example, if you want the equivalent of sine of 360, you're going to have to put in a 720, okay, to get that same value. And so notice, if you have a 1/2 there, the graph is twice as long. Why? Because 1/2 divides into 360 720 times, okay? If I did like 1/3 x, the graph will have a period that is 3 times as long. In fact, it kind of goes off the chart here, okay? So it turns out it's a pretty simple pattern. You can always divide 360 by whatever that multiplier is out in front of the x variable, and that's going to tell you the period. Or if you're working with radians, you can always divide 2 pi by whatever that multiplier is, and it'll give you the value as well. So anyway, in the end, you can combine all these together. For example, if I had something like this, you can see here we have a graph that's been shifted up 2 units. So we have a midline at 2. It has been shifted to the right 60. And because we have that multiplier of 3 out in front of the sign, the period is going to be 1/3 of 360 degrees. And then if I wanted to put a multiplier out here, like maybe I could do 2, I could change the amplitude to be 2. So you can actually combine all of these things together in the same problem, and you can create all kinds of different complex graphs that do all kinds of different things. So that's something we're going to continue to work with, because we will also be graphing by hand, but I don't think we have time to do that now. That's something we're going to have to do in coming sections. But for right now, hopefully you can identify the amplitude and the phase shift and the location of the midline, and hopefully you can now also find the period. And that's really the big takeaway from this investigation.